Welcome to Map 67, Vector Calculus. Today we're going to discuss Section 3.4, Constrained Extrema and Lagrange Multipliers. Let's begin with a brief review of our last section, 3.3, on extrema of real-valued functions. We'll begin with a few definitions. Let's say that x0 is a point in Rn. We'll call it a boundary point of a subset U if we can find a neighborhood of x0 so that part of it is inside of U and part of it is outside of U. Such collection of points we'll denote by partial of U, and we'll call the set the boundary of U. We'll say that a set D of Rn is closed if it contains its boundary. That is, the partial of D is contained in D. The closure of a set U, we'll call it D, is U along with its boundary, partial of U. We'll say that a set D is bounded if D is contained in the open ball D sub R of x0 for some x0 in Rn and some radius r. A set U that is both closed and open is said to be clopen. Here's a main result that gives an example. Fix a point x0 in Rn and a radius r. We'll denote U as the open ball, that is D sub R of x0, which is just a collection of vectors x, such that the length, x minus x0, is less than r. Its boundary, namely S, which we'll also write as the partial of U, is just the set of vectors x such that the length, x minus x0, is equal to r. And finally, its closure, which we'll denote D, is the set of vectors x such that the length, x minus x0, is less than or equal to r. Here's a couple of results. The closure of a set is a closed set. Rn is an example of a clopen set, which is not bounded. Here are a few definitions. Let f be a function that's defined on some open subset R, U, inside of Rn. We'll say that x0 in U is a local minimum if there exists a neighborhood n of x0 so that f of x is greater than f of x0 for all x in the neighborhood. We'll say that x0 is a global minimum if we can choose this neighborhood n to be the entire domain U. We'll say that x0 in U is a local minimum if there exists a neighborhood n such that f of x is less than f of x0 for all x in the neighborhood n. We'll say that x0 is a global minimum if we can choose this neighborhood U, n, to also be the entire domain U. Finally, we say that x0 is a relative extrema if either x0 is a local minimum or local maximum. We'll say that x0 is a global extrema if x0 is either a global minimum or a global maximum. Here are a couple of remarks. Notice that if x0 is a global extrema, then it is a local extrema. Hence, if x0 is a global extrema and f is differentiable, then we expect x0 to be a critical point. That is, the gradient of f of x0 has to be 0. However, not all global extrema can be found using critical points. We saw an example of this in the last lesson. Today, we'd like to discuss constrained extrema and Lagrange multipliers. Let's set things up as follows. Consider a differentiable function f defined in a set U, and we'll denote its boundary by S and its closure by D. So far, we've seen the following algorithm, which allows us to find global extrema on this closed set D. First, determine the local extrema by finding the critical points. That is, take the gradient, set it equal to 0, and then compute the value f evaluated x0. Second, we can find the maximum minimum points values on f by looking at what happens at least at the boundary, that is partial of U. Third, we'll try to compare what we found, the values for the local extrema, that is f of x0, and the maximum minimum values on the boundary, that is f of x1, and then determine which is larger, which is smaller. Step 2 is kind of a weird step because we have to determine the maximum minimum values of f on the boundary, that is with respect to some constraints. We're going to talk about this in a lot more detail today. To set up everything, Let's consider a subset S such that it looks like it's the level set for some differentiable function g. That is, we want to assume that S is in the form the set of x such that g of x equals a constant c. We're also going to assume that S is smooth. That is, that this function g has the property that its derivative, remember this is some matrix, has rank m, which is less than n. Here the setup is our domain U is a subset of Rn, and G maps from U to Rm. So the derivative of G will be an m by n matrix. We're simply assuming that the rank is m. Here's our proposition, the main one for the day. This restriction of f, here we're just looking at f as it sits on the boundary S, has a relative extrema at x0 if and only if there exist scalars lambda 1, lambda 2 through lambda sub m, such that the gradient of f evaluated at x0 is a linear combination of the gradients of the coordinates of our function g. We'll call such an x0 in S a critical point of the restriction, and these scalars lambda 1 through lambda sub m Lagrange multipliers. Now, this is a rather strange proposition, so we'd like to discuss an example next to get a better idea of what's really going on. Let's consider a function f from R2 to R defined by f of xy is ax plus by. Now, of course, if we wanted to find the relative extrema here, we could just simply take the gradient, set it equal to 0, and so on and so forth. However, we're going to do something a little bit strange here. We're only going to restrict inside of R2 to those numbers, x and y, satisfying the criteria x squared plus y squared equals 1. That means we're just going to restrict our function to a circle. And now we'd like to know what are the maximum minimum values of this function once we restrict to the circle. We want to try to compute these maximum minimum values in two different ways. First, let's do this the naive way. Let's realize that S is just the circle. That is, it's the boundary of the unit disk sitting at the origin. For every point in S, we can just use polar coordinates. So let's say that x is cosine theta, y is sine theta. If we do this and play around with some trigonometric identities, we see that f restricted to S is simply the square root of a squared plus b squared times cosine of something. Well, we know the cosine bounces back and forth between +1 and -1, so this means that the maximum minimum values of our function restricted to the circle are just plus or minus the square root of a squared plus b squared. Now let's introduce a second way of doing this, finding these maximum minimum values by using Lagrange multipliers. Notice that we may think of S as simply the level set coming from the function g of xy equals x squared plus y squared. That is, we're going to set g of xy equal to 1, and then now try to understand our function. Notice that both f and g are differentiable on all of R2, so in order to find the critical points for our function restricted to S, we need to solve the following equation. The gradient of f is a scalar times the gradient of g. This is exactly what it means to find Lagrange multipliers. So what we'll do is take the gradient of f, take the gradient of g, and if we set this equal to each other, then this means we can find that x0 has to be a over twice lambda, and y0 has to be b over twice lambda for some lambda we still have yet to find. Now remember that x0 must be an element of R set S. It must lie on the unit circle. So once we make this restriction, we can then solve for our Lagrange multipliers lambda. This means that we can then figure out what the critical points x0, y0 have to be. And if we plug this back into f, we then find our maximum minimum values, which are exactly the same two values that we found using our first method. Let's spend a little bit of time sketching over the proof of the method of Lagrange multipliers. Recall that we're just considering those sets S which are level sets coming from a smooth function g. Again, remember that the derivative of g must be an m by n matrix whose rank is m. First, let's make some observations with this assumption that the rank has to be m. There's something called the implicit function theorem. This basically says if you want to set a function mapping from some subset u of Rn to Rm, and if you want to set g of x equals a constant c, then you can actually solve for m of the n variables. Let's call those variables xj1, xj through to xjm, in terms of the remaining p n minus m variables. Maybe we'll call those xi1, xi2 through xip. So again, we can write the first m variables in terms of a nice collection of p variables. This might look familiar to you from linear algebra. So putting all of this together, there really is some inverse of g, which we're going to call h. H here is a function of only p variables, xi1 through xip. And this is set up so that when you look at the composition g circle h, then you get back this constant c. So again, h here just gives us a nice way of saying that we can locally find the inverse of g. There's some function that gives it to us. We're going to discuss the implicit function there more in a future lesson. Now, notice that the derivative of g is an m by n matrix, while the derivative of h is a n by p matrix. We can now let t be the derivative of g, and we realize by simply looking at the chain rule, if we take the product of t times the matrix, which is the derivative of h, we find the zero matrix. Again, remember that the composition here has to be a constant. That's the way we defined h as the inverse of g. But now saying that the product of two matrices is a constant actually tells us that the rows of t, the derivative of g, must be perpendicular to the columns of the derivative of h. But the kernel of t now really must be generated by the columns of the derivative of h. This is a p-dimensional space. Therefore, the orthogonal complement must be spanned by the rows of t. The rows of t, remember, are just the gradients coming from the different coordinates of our function g. And so saying that we have linear combinations just means that we have sums of the form lambda sub k times the gradient of g sub k, where the lambda sub k's are just some scalars. This now is some m-dimensional space. We're going to come back and stare at this space a little bit more in just a moment. Next, we'll rigorously define the restriction of our function to our level set S by just saying that it's f composed with our function h. Now, if we take the derivative, that is, we take the gradient, then we actually see that we must get back 0. This is because we're trying to find the critical point of f restricted to S. So if the gradient here for the composition must be 0, we use the chain rule to see that the 0 vector must be the product of the gradient of f times the derivative of h. But now we see that this vector, the gradient of f, must be perpendicular to the columns of the derivative of h. But we just found what that space was. That was the orthogonal complement of the kernel of our linear transformation T. But this orthogonal complement is simply spanned by the rows of our derivative. So we see that the gradient of f must be a linear combination of the rows coming from the derivative of g. That is just a linear combination of the gradients of each of the g sub k's. Let's back up for a second to realize what is it that we've just done here. Let's say that we have a function f, and we really have a collection of m constraints. So f here is a function of n variables, and maybe we have constraints g1 of some function must be a constant c1, all the way down through g sub m, which is some function, must be a constant c sub m. Of course, we can put all of this together in a fancy way to just say that we have a subset S. What we like to do is find the relative extrema with respect to these m constraints. And the method of Lagrange multipliers says that we have the following system of equations. The partial of f with respect to x1 must be some scalar lambda 1 times the partial of g with respect to x1 plus some scalar lambda 2 times the partial of g with respect to x1 plus so on and so forth. In other words, we have n plus m equations and n plus m variables. Remember that our equations here have to come from the method of Lagrange multipliers and the m constraints. G1 evaluated must be C1, so on and so forth. The n plus m variables must come from the n variables, namely x1, x2 through x sub n, and the m Lagrange multipliers, lambda 1, lambda 2 through lambda sub m. So now we must solve a system of n plus m equations and n plus m unknowns. Once we do, then we found the relative extrema with respect to our restriction. Here are just a couple of remarks that we're not really going to touch on in this class, but you might see this in a different course. So far, we've only discussed constraints that look like some function g sub k must be equal to some constant c sub k. Such constraints are called holonomic. However, not all constraints are in this form. For example, we might actually say that we want g sub k to not equal to a constant c sub k. Or we might even have an inequality that says something like g sub k should be greater than or equal to c sub k. So how do we deal with these so-called non-holonomic equations? How do we deal with these constraints where maybe we don't have something equals to something else? We might have an inequality. We can actually turn these inequalities into qualities by introducing what's typically called a slack variable. For example, let's say what if we want to say that g sub k of some variable should not equal c sub k? Well, actually, what this means is that the difference g sub k minus c sub k should not be equal to 0. Or maybe we should be able to divide by it. So instead, let's take this inequality, g sub k does not equal c sub k, and let's write it in the form g sub k minus c sub k times some other variable minus 1 equals 0. So now we've taken this inequality, introduced a new variable, sigma sub k, that we'll call a slack variable, and we turned our inequality into an equality. So here on the screen, you can see that there are various ways to turn some of these non-holonomic constraints into holonomic ones. We can think of these sigma sub k's as taking up the slack, so to say, whenever we want to have things like multiplicative inverses or even square roots, because we might want to have things greater than other things. Again, we won't really focus on this here in this class, but this is simply mentioning this because you may see this in other fields. We'll end today by discussing a couple of worked homework problems that do focus on the idea of Lagrange multipliers. Here's our first example. Let's consider a light ray that travels from a point A to a point B, crossing a boundary between two media. For example, this might be light that is just above the surface of the ocean. It then passes through the surface, and now the light is below or is inside the water. We'd like to show that if the speed of light in the first medium is v1 and the speed in the second medium is v2, then we have so-called Snell's law. Sine of theta 1 divided by sine of theta 2 is equal to v1 over v2. You can see a better diagram of all of this in figure 347 on your screen. In order to work this out, let's place our first point A at the position A1, A2, and let's place our second point B at the position B1, B2. Let's say that it crosses the differences between the two medium at some point on the x-axis, which we'll call a point C, and we'll just denote this as x, 0. Well, by looking at the way we've set up our angles, theta 1 and theta 2, you can see that sine of theta 1 is x minus a1 divided by the length, that is going from A to the center C. And sine of theta 2 must be b1 minus x1 divided by the length going from the center C to the second point B. Now remember that the problem said that we want to find the minimum time here. So first let's try to compute the total time it takes to go from point A through point C and down to point B. Well, the time it takes should consider distance divided by speed. Remember, of course, distance is speed times time, so time should be distance divided by speed. Well, going from point A to the middle at point C, we see that the distance is the length from A to C, and the speed is v1. On the other hand, going from the middle at C down to the point B, we see that the distance is the absolute value of C minus B divided by the velocity v2. Now we'd like to minimize this time, so let's take the derivative and set it equal to 0. It's easy to see that the derivative is simply sine of theta 1 divided by v1 minus sine of theta 2 divided by v2. Setting this equal to 0 finds now exactly what we wanted to show, namely Snell's law. Let's consider a second example. A firm uses wool and cotton fiber to produce cloth. The amount of cloth produced is given by the function xy minus x minus y plus 1, where x is the number of pounds of wool and y is the number of pounds of cotton. If wool costs p dollars per pound and cotton costs q dollars per pound, and the firm can spend total of b dollars on the material, what's the ratio of cotton and wool to be produced in other words, to produce the most cloth? Well, the amount of cloth, the quantity Q, is xy minus x minus y plus 1. We'd like to minimize this. But remember that we have to be careful about the cost. Well, if x is the number of pounds of wool and p is the dollars per pound of wool, y is the number of pounds of cotton, and q is the cost per dollars in dollars per pound for cotton, then we see that the total cost should be px plus qy. We like to maximize our quantity by fixing the cost. So using Lagrange multipliers, we see then that the gradient of q must be a scalar lambda times the gradient of c. And our constraint, of course, is that the cost must be equal to the amount that we can spend, namely b. Now let's put all of this together. Since we're saying that the gradient of q must be a scalar times the gradient of c, that actually is two equations. Namely, the partial of q with respect to x must be lambda times the partial of c with respect to x, and the partial of q with respect to y must be lambda times the partial of c with respect to y. Well, the partial of q with respect to x is y minus 1, and the partial of c with respect to x is p. So one of our equations is y minus 1 must equal lambda times p. Similarly, we'll find that x minus 1 must be lambda times q, and since we have to have a constraint on the cost, we see that px plus qy equals b. We can take the first two equations, perhaps the first one, y minus 1 equals lambda p, multiply both sides by q. Take the second equation, x minus 1 equals lambda times q, multiply both sides by p. Add things together, and remember that px plus qy equals b, and we'll find that lambda must be b minus p minus q over twice pq. We plug those into our two equations. We then solve for x and y, and we find that x must be b plus p minus q over twice p, and y must be b minus p plus q over twice q. Remember that the problem asks, what should the ratio of cotton and wool be to produce the most cloth? Here we found how much cotton, that is the number of pounds of wool, we found how much wool, x is the number of pounds of wool, and how much cotton, y is the number of pounds of cotton. So then the ratio of cotton to wool namely y to x, should be p over q times b minus p plus q divided by b plus p minus q. Thanks very much for watching.